All right, so let's start. First, any general questions about anything at all related to this class? Okay. Let's see. Second homework reminder, everything is due by 6 a.m. on Monday. Okay. Next, presentation schedule. So here's what the file looks like right now. So you can see it's almost full. I don't think everybody's here, but there's still 3 slots right here on Monday. Yes?
Oh, sorry, I did have a general question. So
Sure.
When we're doing like the presentation, can we just like use your laptop and just use like Beamer and like a worksheet?
Yes, that would definitely be a good way to go. Be very easy. Yes?
What kind of connection do we need to get onto the projector? HDMI?
Yeah, I'll have this mini HDMI cable, which your laptop has. So
I've got Thunderbolt and USB.
Thunderbolt and mini HDMI are the same,
Oh,
surprisingly. I mean, they're not literally the same. One is a subset of the other or something. I don't know. So, yeah, it's kind of weird. Somehow the connector looks the same, and I think Thunderbolt's just like a faster product. I don't know. I don't want to say something wrong, but they look the same, and you can plug a mini HDMI connector into a Thunderbolt at point on the laptop. Yeah, but you may want to double check right after class just to be sure. Okay, other questions? All right. So again, here's the schedule. Add yourself to this schedule if you haven't already. Is anyone here not on the schedule? Add yourself. Okay. So it's you just go to the project that's shared project. Do you have that one?
yeah.
Okay, good. Excellent. All right, so let's see. Mainly we're going to talk about groups today, but I want to tell a quick story related to Sage and linear algebra and graphs, so John Palmieri, does anyone here know of him? He's a professor in the math department, the head of the grad program in math, and an algebraic topologist, but he said he was at a seminar this week, and the speakers said that they had some graph, and they computed the corresponding adjacency matrix, and then, so you know what I'm talking about, and then they computed something called the Smith normal form of the adjacency matrix, and it's kind of like the reduced row echelon form. It's a little bit different. You do row and column operations over the integers, but it's a similar sort of thing. And they got an answer, and it was really important for the research they were working on, and it took them an hour to get the answer. And the matrix was 80 by 80. So John was like, that's kind of surprisingly slow. So he said he tried exactly the same matrix in Sage. The people were using Mathematica, and it was 2 seconds or something like that. And he was also able to do several much larger examples. So it's a good example of how having graphs, linear algebra, all in one place can be really useful in research applications. But also having it fast makes a big difference. And he was under the impression that to compute the Smith normal form in Mathematica, these people were just took a book on Smith normal form and implemented it from scratch because it wasn't just a function available or something. Or if it was, he didn't look into it too deeply. If it was available, it was very, very slow compared to what was in Sage. So that is a little story that just randomly somebody told me yesterday. Or John told me yesterday. Okay, so groups in Sage. It was really hard to talk with a cough drop right now. Try and get a trash can. Sorry. So Sage can compute with groups. Here's what's going to happen. So I'm going to show you a quick example. You've already seen several. Then I'm going to step back for a minute and just give you some background about groups in case you don't know very much about them. I'm going to assume you've never heard of a group in a moment. And then I'll give you a whole bunch of situations and examples where groups come up fairly naturally in the context of math and show you examples of using them in Sage. Okay? So that's the plan. First, I'm going to just give you the whirlwind 1-minute tour of groups. You can compute a lot of things involving a lot of different groups with Sage. This is the reference manual index for the chapter called Groups. The main point is that it's really big. And despite there not being a lot of group theorists, so people who specialize in group theory, as Sage developers, we still have an enormous amount of group functionality. And the reason for that is that when I was building Sage at the beginning, I wanted some functionality really for coding theory that was provided by a program called GAP, Groups, Algorithms, and Programming, which is right here, GAP system group. So this, I showed you this website once before. This system was developed by a large number of group theorists over decades. And so it has a huge amount of development work in it to allow you to compete with groups. And in Sage, much of that functionality and much more is made available. So we get to stand on the shoulders of GAP in implementing the group theory functionality for Sage. And after 7 years, it starts getting pretty refined. So there is a lot for working with groups. Here's just a very quick one-page example of working with groups. So if you type groups.tab, you'll see different collections of different types of groups. One of them is groups.permutation, and then those are a whole bunch of permutation, families of permutation groups. This is kind of similar to the situation with graphs, where you type graphs.tab, there's a whole bunch of different families of graphs with different parameters, and you enter a parameter and then it tells you or gives you that graph. So there are groups like alternating groups, cyclic groups, dihedral groups, et cetera, et cetera. And so one example, which I'm going to show you here, is called the dihedral group. This is the group of all symmetries of a regular polygon with d sides. So in this example, 4 sides, a square. So in general, you have a whole bunch of different sides, but that doesn't look sufficiently regular, but just a perfect square. And so there are a bunch of symmetries, so you can kind of keep track of them by imagining labeling the 4 corners of your square. It kind of sounds like graphs, but here we're viewing this as a square, as a rigid object. And you think of all ways of picking this thing up or somehow transforming it in a way that sends it onto itself, but it could possibly predict the corners. So for example, you can flip it, you can reflect it vertically, or rather you can reflect it across this vertical line of symmetry. You can reflect it horizontally. You can also rotate it. So there are different symmetries of a square. In general, if you have something with d sides, there are 2D symmetries of that object. And the group of these 2D symmetries is called the dihedral group. So here's the dihedral group of order 4. You can create it. You can list all of the elements. And I will tell you, I will remind you, since I did very briefly try to explain this notation, but I'll remind you of it in a moment in great detail, what these mean. But each thing that's listed here, like 2, 4, 1, 2, 3, 4, this describes a way of taking this object and mapping it to itself in such a way that the corners are permuted. And these are generators. So many algebraic objects have a collection of elements in them so that everything else can be got by just multiplying that small collection of elements together. So these two things do it. And you can do arithmetic with the generators. So A and B are these two ways of flipping around this object. And if you do A star B, that means do one of them, then do the other. So the result is what happens if you do both. Okay, so that's just a really simple example. And you can change 4 to something else. Somebody make up a number, like a different number of sides for an object that you like. 8, an octagon. So there we are. The group will have order 16. And we'll get a bunch of permutations of, so the elements of the group, they're described by how they permute the vertices, or the corners, as it turns out. Because if you know exactly which corners go to what other corners, that completely determines how you're mapping an object to itself via an isomorphism. So, or a symmetry. And so like there's one that sends 1 to 7, 5, and 5 to, well, obviously it's 7. But these are all of the permutations, and then there's a different list of generators. One of these is a rotation, that's what this one means, and the other one is some sort of, well, I don't know what I mean, It's some sort of flipping, but apparently involves all of these.
That's because it's the flipping about the vertical axis.
Ah, is it? Oh, for an octagon.
If you
Oh, yeah, yeah.
start-
That makes sense. So, thank you. So if you draw an octagon, like that, and then I guess label it 1 and 8, maybe 2, 7,
3, 6,
3, 6,
4, 5.
4, 5, and then flipping it across that vertical axis gives you the second one, and then the first one is counterclockwise rotation. Well, one goes to 2, and maybe it's clockwise in South Africa, but in America it's counterclockwise. In America it's counterclockwise. Okay, so there we are. Good. So yes.
To get the cycle notation to work,
Yes.
where do we need to flip 3 and 4?
Probably. Let's see. Let me let's switch back to the other one and get things to match up. So here they are. So 1, 2, 3, 4. Yeah, I think we should switch 3 and 4. Then it will be just a rotation counterclockwise. Thank you. Okay, good. So that is a very quick thing, and there are a lot of methods that a group has. Let's see, length of Dura G, 349 methods. So given a group G in Sage, there are 349 things that you can do with it. One of them is get the generators, but there are others. Okay, so now let's make sure that everyone understands this cycle notation, since it's pretty hard to do anything with groups without understanding this. So I'm going to explain it, and then we're just going to do a little exercise involving it. So first I'm just going to explain cycle notation. We're going to fix ideas and think only about permutations of the integers from 1 to n. Yesterday, Wednesday, we were often considering 0 through n minus 1 in the context of graphs, but it's pretty similar. So the notation in Sage A1, A2, dot, dot, AK in the context of permutation groups means the following, and also in like all of mathematics, it means the permutation that sends A1 to A2, A2 to A3, AK minus 1 to AK, and then finally AK to A1. It's a completely made up notation. It's just very convenient. It's a compact way of representing a cyclic permutation of some of the numbers. And it doesn't do anything at all to anything that isn't listed here. Okay? So if n is 100 and the numbers here are just like 2, 3, 1, 4, then this means it's the permutation that sends 2 to 3, 3 to 1, etc., and it doesn't touch anything else. It just leaves everything else fixed. Okay? So this is a very special type of permutation, a cyclic permutation that leaves everything fixed except some collection of things that it just cycles around and around. It turns out that every permutation there is can always be written as a product of these cyclic permutations. Okay? So first, let's do this quick exercise. Quickly shout out what 1 goes to under this particular cyclic permutation. Okay, what about 2? What about 3? What about 4? Perfect. Okay, next, disjoint cycle notation. If you have a permutation described as above, so 2, 3, 1, 4, and then another permutation involving completely different numbers, 5, 7, 6, then you just stick them together, and that means the permutation that, since it just does both of them, right? Because they're completely independent of each other. So it's like multiplying them together. And so this is a permutation that sends, well, for 1 through 4, it's exactly as above. What does it send 5 to? 7. What's it send 6 to? 5. And what's it send 7 to? 6. Perfect. So there we are. So that's what this one does. And if you have, now let's make it even more fun. So let's take this permutation, 5, 7, 6. So let's call that A. And if we do, let's make another permutation, 1, 2, 5, 7. Okay, these are 2 different permutations. And they're elements of what's called the symmetric group on 7 symbols. And we can actually make them elements of that by following. You have to give valid Python notation. I guess just do that. Okay, so there's A and B. And now let's figure out what A times B is. This is supposed to mean you first do A and then you do B. Or maybe it means first do B and then do A. I'm not going to tell you which. We'll figure it out, okay? So let's figure out what the product of first do B, then do A is. By that I mean, so what we're going to do is figure out where each of the numbers from 1 to 7 goes under first doing B and then doing A. Oops. Okay, so we have A and we have B. What happens if you take B and apply it to 1? Good, 2. Because B is the permutation that sends 1 to 2, right? So now if you then take 2 and apply A, what do you get? 3. Okay, so there we are. All right, what's the next one? What does 2 go to? Just give me the final answer. 7. Okay, what does 3 go to? Excellent, 1. Okay, what does 4 go to? Excellent, 2. What does 5 go to? Excellent. What does 6 go to? Yep. And finally 7. Oops. 4. So 7 goes to 1 under B, and then under A it goes to 4. Okay, and now let's write this bottom one as a product of cycles. Okay, disjoint cycles. So what we'll do is we'll say, okay, 1 goes to something. What does 1 go to? 3. Now what does 3 go to? 1. Okay, so that's our cycle. And now I'll make another one. What does 2 go to? 7. Okay, and what does 7 go to? And what does 4 go to? Okay, so that cycle's done. Is there anything left? 5. What does 5 go to? What does 6 go to? Is there anything left? Nope, so we have everything. So that's the answer in disjoint cycle notation. And that's how it works. So permutations of the numbers from 1 to n, you can always write them, no matter what they are, you can always write them via the procedure we just did at the bottom as a product of disjoint cycles. And when you have them written as a product of disjoint cycles, you get back a permutation. There's like a one-to-one correspondence between permutations thought of this way and thought of as products of disjoint cycles. But the bottom one is more compact, and when you see it, you instantly see structure in the permutation. You know that it flips 5 and 6. You know that it, since it has like it makes 2, 7, if you do it over and over again, you know what it's going to do, basically. Whereas if you look at this, imagine if instead of 7 things were in this table, it was 100. It would be very hard to see any structure. It would just look like a list of 100 random numbers. But if I gave you that same permutation of 100 things as a product of disjoint cycles, like the bottom, you would see structure in it instantly. So you can see the bottom is a vastly better way of representing permutations. And that's why it's that way in Sage. Okay, now let's evaluate this product and see if it has anything to do with what we just computed. It does not. And what does that mean? It means maybe the order is the opposite of what we just did. And indeed, look. So B star A means first do B, then do A. It's completely, there's no a priori reason why A star B, or like, basically it's a convention which one's which, and in Sage it's a particular convention, so watch out. Some people choose one way, some people choose another. So it turns out that in Sage, what we just computed was B times A in the group of permutations. But it matches up and we got the right answer. Okay? All right, so that is the basics of permutations. You can write permutations as a product of disjoint cycles. And here's another thing. So let's see. I'll just put this here. So, sorry. So the symmetric group, that's one specific type of group. A group, I've never really formally defined it, but a group is a fairly easy thing to define. It's a set and an operation on the set, a way of combining two elements of the set to give you another element of the set. And then there are some axioms that are satisfied. It's fairly easy to define them compared to some things, so maybe I should just tell you. So a group is a set, and then you have a way of multiplying two elements of a set to get another one. And the axioms are A times B times C is A times B times C, the associative law. And then there's a one element in G, such that 1 times A equals A times 1 equals A for all A. And then there's one other axiom, which is for every A in G, there's an inverse. There's a B with A times B equal to 1. And that is what a group is. It's a set equipped with a way of multiplying elements such that these three axioms are satisfied. And an example, a very representative example of a group is the set of all permutations of the numbers from 1 to n. And that one's called S sub n. So S sub n equals all permutations of 1 through n. And it turns out that every single finite group, so anytime G is finite, it's a subset. It can be represented as a subset of this, with the group operation being composition of functions. So this is kind of the prototypical finite group. And in Sage, you make it by saying symmetric group and then giving n. Okay. How many permutations are there of n objects? Well, it's just a basic counting problem. You choose, if you're going to make a permutation of n things, you choose where 1 goes, you choose where 2 goes, and at each point you have one less number of choices to choose from. So there are n ways to choose where 1 goes, n minus 1 ways to choose where 2 goes, etc. And so when you multiply all those possibilities together, you find that there are n factorial different permutations. So for example, the symmetric group on 4 symbols, I'm creating it right here. And then it has cardinality 24, which is 4 factorial. Factorial of 4. And here are the, explicitly, here's every single permutation on 4 symbols, numbers from 1 to 4. And the cycle we were playing with at the very beginning is 2, 3, 1, 4. Notice that you won't literally see 2, 3, 1, 4 below, though there's something that is equivalent to it below. It's somewhere down here, right here. Because you can always just, you get the same permutation if you write it as, say, 1, 4, 2, 3. It defines exactly the same permutation. You can always move the cycle around. Okay, and you can make, like we can make a big version of this. So this has cardinality very large. It doesn't literally, so if you did list of S, you would be in trouble maybe because that's so big. Maybe I'll make it even bigger. See, it's not literally storing every element of the group in the computer because we would have exceeded the memory by far already. It knows, so when you say symmetric group 20, it has kind of an abstract understanding of what that means. And it allows you to do, you can ask questions about it, make elements in there, do things. But if you try to do list of S, you'd be in big trouble at this point. I better change it back before somebody does that. Okay. All right, we already did this exercise.
Would Sage Mathbot try to compute it if you tried to get the list?
Yep, and you'd run out of memory and it would crash.
What happens when it crashes?
Right now, a worksheet, when the process, so when the Sage process crashes, the worksheet will simply appear to continue running forever. But the actual process has crashed. So it doesn't ever, basically you never get any message that things are bad. This needs to be changed. Instead, it should tell you that it crashed. If you try to evaluate additional code, then it will automatically restart the worksheet and it just starts working again. So basically it heals itself, so to speak, but it doesn't give you a clear indicator that it has run out of memory and crashed. And if you just run out of memory, depending on what code is running out of memory, it may do a wide range of different stupid things. Programs tend to behave very badly when they run out of memory. Because what happens is they ask the operating system, I need some more memory. The operating system gives them back, they expect a pointer to some more memory and they get back 0 instead. And they're supposed to check that and then do something sensible. But often you're so deep in the code that there's no sensible thing to do. And And so you just say, screw it, you don't even bother checking your return code, and then you end up trying to use that memory as if it's valid, even though it's not. So the program seg faults. So that's not uncommon in various code. But it's often very difficult. Exactly the part of the code that's allocating memory is often has to be very fast, and so you don't want it to be checking for validity of the results. And even if it does check, it's unfortunately can be very hard to report back up the stack that you had problems accessing memory or allocating memory. So bad things happen, unfortunately. Okay, a subgroup, just throw in one more definition. So a group is a set like this. A subgroup is just a subset of a group G that has the same axioms using the same product. So if you just take this product and restrict it to a subset of H, and it's still a group under that product, then it's called a subgroup. It's a pretty natural choice of language. It's a subset of a group that is also a group under the same operation. And in Sage, if, for example, you make a group like we did above, and you want to make the subgroup generated by certain elements, you can say subgroup, and then you give a list of the elements, and it gives you all possible ways of combining together those symmetries, because they often are symmetries, to get you some group. This is the subgroup generated by those. So the original group S we were considering above, of all symmetries or of all permutations of 4 numbers, if we take the 2 permutations A and B that I've defined somewhere, and can't remember where actually. Sorry, it's a little bit lost here. So the A and the B are given right here. I'll just copy and paste them again. Okay, so just redefine A and B. And now you can, basically we're asking the question, what if you take all possible ways of multiplying together A and B? What do you get? It's kind of neat because you could do this in general. If you have some object and you wonder, you could see a couple of symmetries of it. What happens if you take all possible ways of combining those symmetries? Because any time you take one way of, taking an object and putting it onto itself, any symmetry of an object and combining it with another one, it's a third symmetry. And so neat to see what is generated by all the symmetries of an object. I'll show you a situation that you're familiar with where this comes up, and it's pretty interesting in a minute. But in this case, these two give you a subgroup of order 12, which is given right here. All right, so now let's stop for a second, and the next section is I'm going to show you various places that groups come from. And this will be easy for a moment because my first example is graphs. Graphs are a source of groups. And in fact, this is exactly what we saw on Wednesday. If you make a graph, any graph at all, ever, then you can ask for all the symmetries of the graph. That is all ways of mapping, all ways of permuting the vertices of the graph so that edges get sent to edges. So here's a graph I just made up, wheel graph on 5 vertices. I guess it would look more like a wheel if I made it on 6 vertices. Oops. There, that looks more, I don't know, that's not really a good wheel. But in any case, you can ask for its automorphism group, and there it is. And I'm a little scared to list the generators because I don't know how many there are, so I'll do g.cardinality. There are 10, okay, that's safe. And here we are. By the way, I think that the fact that there are 10 here, that's a 5-sided figure, so I think this is really just the dihedral group of order 10 on 5 things. I wonder if we can figure that out. So I can also do groups.dihedral or groups.permutation.dihedral on 5. Remember, that was our dihedral group. G.is isomorphic. So one of the many functions you have with a group is one that will tell you whether one group is isomorphic to another group. And I realized that I never defined the term isomorphism. But what that means is that you have a set theoretic map, just a map of sets from one group to another which has the property that if you multiply two elements and then map, it's the same as mapping and then multiplying the two elements. In other words, the group structure, that is the way the multiplication works, is respected by the map. It's not just some completely random map from a set of cardinality 10 to another set of cardinality 10. It's one that respects the group structure. So let's ask whether or not there's an isomorphism like this. And the answer is true. So the automorphism group of the wheel graph that we found, in this case, is exactly the same as the, or is algebraically, from the point of group theory, the same as the group of all symmetries of five-sided of a pentagon. Okay, so that's just a little example of something you can do. And you might start wondering about things. How many groups of order 10 are there up to isomorphism? So just like with graphs, there's a question. Can you enumerate all of them? How many are there? What's their structure like? And there's lots of theorems that help you do this. I'm guessing there's 2. But I'm not sure. I don't actually know. That said, there is one of the deepest and most important theorems of the 20th century is called the classification theorem for finite groups, or finite simple groups. But there is, in fact, a very deep and complete classification of all finite groups, which is really amazing. So basically what happens is, given a group that's finite, so the number of elements in the group is finite, there's a way of breaking it up into simple pieces. And then you take the simple pieces, and there are infinitely many possibilities for the simple pieces, but they fall into a collection of families. One of them being, well, it's not exactly the symmetric group Sn, but a subgroup of, it's almost the same as Sn. So that's one of the families. And there's a couple of others. And there are infinite families of groups that you get via various constructions, kind of like this one that we were doing right here. And then you find a couple of other funny groups that just don't fit into any of these families, but they're really, really big and terrifying. In fact, the biggest one of all is called the monster simple group. And monster. And there are a lot of questions about it. But in any case, there are all these exceptional groups, as they're called. And amazingly, people were able to prove via a huge amount of work that every single group, its simple pieces are either one of the infinite families or it's one of the exceptional groups. And there are no other possibilities at all. And then they started studying these funny exceptional groups and came up with all kinds of weird and surprising conjectures about them, which were subsequently proved, many of them at least.
The interesting thing is that there are only 26 exceptional groups.
Yeah.
That's it.
It has nothing to do with the letters of the alphabet. But yeah, there's exactly 26, and then there's no more ever. So it's an amazing, deep result that occupies many pages. Okay, more places where groups come from. So they come from graphs. Groups also come from games. So an example game is the Rubik's Cube, or puzzle. I mean, games, there are a lot of different games, and Rubik's Cube is a puzzle. So games and puzzles would be a better title. So in fact, in Sage, you can say groups.permutations.Rubik's Cube, and you get back the Rubik's Cube group as an explicit permutation group, just like the other ones we were considering. It's a subgroup of the symmetric group on 48 symbols. And I'll tell you where that 48 comes from and so on in just a moment. It's a pretty big group. This is the group of all possible, so if you take a Rubik's Cube, and then there are various moves you can do, like twist this, twist that, etc. The collection of all ways that you can go from your starting position to some other position, that's what the elements of this group are. And but I'll make that completely precise in just a moment. In fact, actually, I might as well make that precise now. So if you did a Google search a day or two ago, it was the anniversary of Rubik's Cube. And so right above the search box, there is a Rubik's Cube. And I've just embedded Google's Rubik's Cube in this worksheet. And so I'm actually moving this. So here's how you get elements of a group associated to the Rubik's Cube, to the moves of a Rubik's Cube. So what you do is you label with the numbers from 1 through 48 each of the little spots, like this little white one, you maybe label it 1, and then this green thing 2, and then 3, and you end up putting 8 labels on each face. You don't do anything with the center one because it doesn't move. As far as, well, it's not necessary to keep track of it. So you just put 8 numbers on this face, and you put 8 numbers on each of the other faces. And how many faces are there? 6. And 6 times 8 is 48, so that's where the 48 came from above. And so each move, so there's a couple of generating moves, like flipping this face around. I guess it's a little hard to do. Flipping that face around, etc. So what you do is, when you do that move, it permutes the numbers from 1 to 48 around. Okay? Like literally, if you put 1, 2, 3 right there, and then you did the move, then you had some numbers on the side over there, and so 1, 2, and 3 go to whatever numbers you put over there. Okay? So if you labeled the faces of the Rubik's Cube with numbers from 1 through 48, then each way of changing the position of the Rubik's Cube would be a permutation of the numbers from 1 to 48, right? And in fact, if you started with a blank Rubik's Cube and then scrambled it, let's say you set things up so that the blank Rubik's Cube is the permutation that sends 1 to 1, 2 to 2, 3 to 3, etc. Then when you scramble it, it's another permutation. And if you, so this group that we're considering, it has generators, which are labeled R, L, F, B, U, D. And they're just specific things like twisting the right face, twisting the left face, etc. You can look at a table in Wikipedia that shows what those are. Then the problem of solving the Rubik's Cube is given a permutation that's allowed. So it's some complicated product of R, L, F, B, U, and D. Write it as a product of R, L, F, B, U, and D. It's literally just given an element of this group, write it in terms of these generators. And you want to do it in a short way, so that it's the least number of twists, possibly. But when you solve the Rubik's Cube, all you're doing is taking a general element of this group and then writing it in terms of generators of the group. That's what you're doing. And by the way, here's the cardinality of the Rubik's Cube group. This is the set of all possible positions that a Rubik's Cube can be in. It's that big number up there, which is, when you factor it, it's 2 to the 27 times 3 to the 14 times 5 cubed times 7 squared times 11. Let's see. There was a question, what is the shortest, how long, in other words, how many twists are needed to solve the Rubik's Cube? I think that's been solved by now. Do you know? Yeah. It was a pretty recent thing. Yeah. So, yeah, it was an unsolved problem, I think, until a year ago. Given an arbitrary position of the Rubik's Cube, what's the absolute minimum, or what's the absolute maximum number of steps that are absolutely required? So, you know what I mean? The question is clear. So the point is that it was very, very recently proved via enormous calculation involving some group theory that you can solve any Rubik's Cube in 20 or less twists, according to Simon's memory, which I know is around 20. So people kept getting it down, and now it's 20, and I guess that's best possible. So it's these generators. So really solving is about writing in terms of these generators. There's a whole bunch of special purpose code in Sage that can solve in various ways, by the way. Okay, so that's another example of where a group pops up, but there are lots and lots of puzzles out there where if you want to systematically be able to solve them, if you can figure out how to represent the moves of the puzzle as elements of a group, then you can solve the problem by simply writing an arbitrary element of the group in terms of generators of the group. And that question is called the word problem, being able to write an element of a group in terms of generators of the group. And word problem, I think, should be I thought it was a method. I guess maybe it's not always. Currently, there's no method word problem, but that's what it's called, at least abstractly. Okay, more examples. Where do groups come from? Here's another place that groups come from. So remember we considered finite fields very briefly recently on Monday. Well, they're also an interesting source of groups in various ways. So here's an example of a finite field. You take the numbers from 0 through 4 inclusive. And in Sage, you make it by saying GF5. GF stands for Galois field, because Galois, this kid who did an enormous amount of amazing math in France in the 1800s, was named Galois. And he probably was interested in finite fields. In any case, these are the elements, and you can create 2 elements in there and do some arithmetic with them for fun. Here's an example of doing this. So I make A be the element 4, B is the element 2. A plus B is 1. The reason, because you add the numbers together, you get 6, but then you reduce modulo 5. That is, you divide by 5 and take the remainder. So you take 6, divide by 5, then the remainder is 1. And likewise, for multiplication, if you multiply 4 and 2, you get 8. If you divide by 5 and take the remainder, you get 3. And that's how arithmetic works in these finite fields. And again, the finite fields are extremely important in coding theory and a lot of applications in computer science. So here's an example of a group. You take all 2x2 invertible matrices with entries in a specific finite field, and that's a group. And in Sage, you can create it by saying GL2F5, or F can be any field, but any finite field. So just to write something on the board, it's the set of all 2x2 matrices A, B, C, D, where A, B, C, and D are in our finite field. And you also require that the matrix is invertible, so AD minus BC is not equal to 0. So it's just a bunch of 2x2 matrices. An interesting problem is to figure out how many there are. If you think about it, it's not quite obvious. You have to do some linear algebra. It's easy to compute the number of 2x2 matrices. There's 5 choices for A, 5 choices for B, 5 choices for C, and 5 choices for D. So that's 5 to the power of 4. But some of those are not invertible. So how do you figure out how many of them are invertible? Any thoughts? How about an easier question? How many possibilities are there for the first row of this matrix? So 2, there's more than 2, because, like, can you tell me anything that cannot possibly be the first row of an invertible matrix? 0, 0, exactly. So you can rule that out, but anything else could be the first row of a 2x2 invertible matrix. So how many pairs AB are there except for the 0, 0 pair? How many?
6.
And we're choosing them from F5. Okay, so let's see, there's 5 choices. If we didn't even care about the 0, 0 condition, it would be 5 times 5, but minus 1. So what number is that? What number is that? 24. Excellent. So there's 24 possibilities. 5 times 5 minus 1 for the first row. And then you have to choose the second row. And obviously you don't want the second row to be 0, 0. But really the condition on the second row is that it's not a multiple of the first row. So how many possibilities are there? Remember, there's 25 vectors, and you have to throw away all the multiples of the first row. How many multiples of the first row are there? 5, exactly, because the first row is just a vector, and there's 5 possible multiples of it. 0 times it, 1 times it, 2 times it, 3 times it, and 4 times it. So you take those 25 things and throw away 5 of them, leaving 20. So there's 20 possibilities for the second row. So 5 times 5 minus 5. And there you are. So you get to choose them independently. So it's 24 times 20, 480. So that is what we just computed as the number of possible invertible 2x2 matrices with entries here. And we could be completely wrong, but we're right, because look, 40 is the cardinality of this group. Okay, so just a little, well, it's an illustration partly of how Sage can be useful if you want to do a similar calculation, but now let's say for 3x3 matrices, and you need to double check your work, you could do the calculation, just change the 2 to a 3, and see what the cardinality is. and you'll get something. It's going to be really big. There. There's some formula that would yield this. And I'm sure anyone here could figure it out. You just have to think about it. Okay, I'm going to change this back to 2. All right, and just like with our permutation groups, there's generators. That is a certain, hopefully small subset of elements of the group. So every other element can be written in terms of those. Generators are kind of like a basis for a vector space, where you can write any element of the vector space in terms of elements of that basis. Except generators might not be as good in that there might not be a unique way to write things in terms of generators. Okay. Let's see. There's lots of other groups you can get from matrices. So instead of 2 by 2, look at all the 3 by 3 matrices, 4 by 4 matrices. Instead of just being invertible, you could require the determinant to equal 1. And that actually gives you a group, because the product of 2 matrices of determinant 1 has determinant 1. The inverse of a matrix of determinant 1 has determinant 1. So you have that. And there's lots of other conditions. If you know about bilinear, if you think about the dot product, you can look at matrices that maybe somehow respect the dot product or similar bilinear form. So you could consider symmetric matrices, maybe. You could consider upper triangular matrices. If you multiply 2 upper triangular matrices together, it's upper triangular. So you have that. And there's a bunch of other things you can do. This starts getting into something called representation theory. So maybe you've never heard of it, but representation theory is this enormous area of mathematics that involves basically looking at groups that involve matrices. And it's extremely powerful. You get to combine lots of information from linear algebra with group theory in one place, and you get a lot of insight into things that look really random at first glance. Okay, and I will end there since it's about a minute early. So let's stop.
I would have before that.